Oh, well, thank you, everybody, being here. What I'm going to do is, by some examples, discuss various aspects of two essentially different environments, well, potentially essentially different environments for doing consulting. So put the biography in so you'd have something to check against what I actually said. So you should start with a joke, so I'll start talking about me. I just wanted to show you where I'm coming from, and that is that I started off with a PhD in very pure mathematics. I knew no computing, no statistics. LaTeX hadn't been invented then. Well, it may be invented, but it wasn't being used then, wasn't distributed. From there, I got a job at the Australian Bureau of Statistics. I went through various employers, picking up on the way a part-time Masters in Statistics at ANU. On the strength of that and my experience, I became an academic at the University of Newcastle for about 11 years. Went back to doing some more OR type stuff. And I was a partner in a small consulting company. I worked in the finance industry. I was in Sydney in the statistical consulting. I was the statistical consulting section in Sydney for a while. Biostatistics at Monash. And now I'm a freelance consultant in my own company. My sort of introduction to consulting was, the first time they let me out on my own was when I was working at ABS, was to design a survey for the National Library. And the question was, how many items do we have in our library and what physical state are they in? That seemed to have worked, at least they seemed satisfied, so that's what I did. The important thing there is to realise what do you sample. Immediate thought is the catalogue, but you don't sample the catalogue, you sample the physical thing they can't change, which is the bookshelves. The next one I did was labour force household survey data. I looked at I was asked to do a regression model of length of duration of unemployment against all sorts of characteristics. And if you look at those sorts of pictures, you see sort of, you have a characteristic like here, it might be age going this way, length of unemployment going that way, and you get all the points in the bottom left-hand corner, and it's a spread of points, and they asked me to fit a line to that. And I said, don't be ridiculous, that doesn't look like a line. So I thought about it some more, and I realized that this was actually a survival analysis problem with time reversed. Because in the survey now, you look back to see when you were last employed. The problem with this was that I hadn't learned any survival analysis by then, so I was sort of working in the dark quite a bit there. So that was sort of my early gropings before I actually knew very much. Maybe still gropings, I feel like that sometimes. Sometimes one's the only statistician in sight. And my first job away from the ABS at the Department of Defence, I was doing what could be called operations research. So one of the things I looked at was combat modelling. I won't go into any of the details. It was interesting. It was probably important. It was the first place I came across what I think of as non-response problems, which is not the usual sort. It's non-responsiveness of the client to what you tell them. In this case, it was, we told them that the ship would get blown up about 1/3 of the time under the condition they were talking about, and the Admiral was not very pleased with this and wanted to argue with the conclusions. I won't say any more about that, except to say when I was writing the report, since I've talked about the difference between some of these things being on the basis of what you can publish and what you can't, when I was writing the report, I realized that my report was going to be classified above my clearance level. So I wrote something that I now cannot read. Well, I can't read anything I wrote at that time now because it's all classified and I'm no longer cleared. But it's just sort of, I deliberately didn't write the last bit because I knew it would be classified top secret when I was only cleared to secret. And that's what happened. A longer term project, I did that project, the first one I did with a physicist and a chemist, nuclear physicist and a chemist. The safety models. So I looked at safety models. The main safety model, and I'll talk about this a bit in a minute, is safety on firing ranges. But another thing that was related to that, at least conceptually, was about the reliability of the F-111 ejector seat. For those of you that don't realize, F-111 is a large fighter bomber, I think you'd probably call it, which Australia had quite a lot. They were used in Vietnam. And the question was for the reliability of the seats. This was significant to me, this problem, because it was my first encounter with using Bayesian statistics, because you have essentially what it boils down to, the thing works if the rocket that the pilots or the crew are sitting on fires. So it all depends on the reliability of this rocket. The rockets are incredibly expensive, so only 10 have ever been fired, except in emergencies. And so you had this question, well, how reliable is an estimate based on 10 when nothing happened? Well, I realized that Bayes was useful for that. And that was much later. That was useful in some of my work in finance. So, because we were talking about failures of highly reliable companies, AAA rated companies. Anyway, I'm not going to talk about that. So back to the range safety problem. Here, over a period of a couple of years, I had developed models for realistic ranges where we could use surveys at about a meter scale of the terrain and firing ranges. We had data on ricochet, and we also had real data on aimer errors. You'd think that aimer error was the thing that causes most danger, but in fact it's not. It's the ricochets that cause the problem. And we were able to produce pictures like this. Here, at this end, is somebody firing, kneeling, shooting at a target 100 meters away with a larger value of the standard deviation of the aimer errors. This is a simulation. And we just sliced it so you can see the progress of the bullets through the air above the range. And this was a question about a range at Majura, which is close to Canberra Airport. And the question was, could airplanes fly over it? Was it safe? The answer is no. All right, so we've done lots of stuff like that. That was a lot of simulation, Fortran, and things like that. Serious simulation going on there, 48 hours worth of per run. But there was another problem, which was of a different nature, and I think quite interesting. When I was by now I'd moved on to the University of Newcastle, and I was asked to look at this problem, bearing in mind that I had models for range safety. Oh, sorry, back. Probably that, yes. This was the Tully Battle School. That Tully is between Townsville and Cairns. The idea is it's a place to train infantry in the jungle. And so they don't want to have this sort of set up range where you fire at a fixed target over there. They want to be able to sort of move through the environment and shoot at things that targets pop up and things like that. So why is that of any interest? Well, if you look at the map of the terrain, can we read it? Yeah, the number up above my hand there is 500 and something meters. The scale here is a 1 kilometer grid, and the land down here, it's a bit blurred, so it's, but that's about 100 and a bit down there. So between here and up there is a 400 meter. This is sort of a bowl. This, you know, quite steep sides, cliffs, and so on. And it's a decent size. So what was the problem? Well, the problem was that they didn't want to damage the environment too much. They wanted to use it, but not damage the environment too much. All around it, there was a state forest, which is not owned by the Commonwealth, of course, but owned by the state. And it was illegal to shoot anything into those areas. The safety on firing range is managed by the use of things called templates, and these are mandated by regulations, so they're legally enforceable, quite important things. And the problem was that same picture, but with these templates drawn on in colour. And the idea of the template is it goes out to the range of the weapon firing in that direction, like this light green one, and the arc that you're allowed to fire over, and then we add a bit for ricochet. That's the idea. I won't go into the science behind that because it's a bit dodgy and historical and so on. But anyway, those are the rules. And the problem is that this one, for example, goes outside the boundary of the Commonwealth land, and is indicated by the purple bit up there. There's another one over here, and similarly. So it's saying you can't fire anything on this range because there's not enough space to fit the templates in. So, could you buy the land next door? No. State government wasn't open to that. Don't want to use fixed firing ranges. I've talked about that. But I didn't mention that that actually causes more environmental damage than wandering around shooting in all sorts of different directions, because the trees don't get a chance to grow back once you've shot them to pieces. And if you have a fixed column, you chop all sorts of stuff down. They're pretty destructive, these bullets. I won't go into the second one. It's just people, that wasn't acceptable to the army. So what do we know? This is before I'd been there. I'll come to that in a minute. The terrain was extremely rugged. You had to stay in a valley, so you weren't going up the sides at all. It wasn't feasible. They're cliffs, and, you know, couldn't go up there. The vegetation was extremely dense. So, thinking about it, what could we do? Well, one possibility was I knew how to model, you know, ranges, and you could use the fact that it's got this sort of bowl shape, and maybe that contains everything. That was possible, but that seemed a bit like overkill, because you'd need a survey of the land, and doing a survey in the jungle is not sort of really what you want to do. But there was a simpler solution, perhaps, and that was, it seemed pretty obvious that, you know, they're not firing explosive things, they're only firing bullets. So there's a good chance that a bullet's going to hit something before it's gone too far. And maybe we can use that to demonstrate the safety. You know, we're containing everything. So the question, what it means is a model. What must it answer? How many bullets go how far before hitting a sizable object? Or even a not terribly sizable object, actually, but because if it hits something small, it can tumble, not go very far. But certainly if it hits something big, it won't go very far. So what sort of model? We actually came up with this idea. So how do we work out how far a bullet goes? The idea of this model is, this picture is that big circles represent trees, all the same diameter. The coloured dots are the centres of the trees. The arrow there indicates the flight path of a bullet. So the question is, how far does a bullet going along that flight path? When we ignore whether it hits the ground or not, we forget all about gravity. We just talk about rays of light, sort of thing. And so how do we know when a bullet will hit an object? And it will hit one of those trees if the center, shown in green, lies inside that rectangle, which is as wide as one tree diameter. So bullet traveling along that path hits these three things, assuming you can go through them, of course, if and only if the centers lie inside the 1 diameter wide path. Now that was the sort of, what that means is that if you, a reasonable model is that tree centers are distributed maybe sort of like a Poisson process in the plane. I mean, that's not right, but it's a place to start. And suppose we knew that, what is the distribution of the distance to the first object you hit? Turns out that the probability falls off very rapidly with the distance. And I can't remember if it's exponential or not. It was a while ago since I did that, but it's good enough anyway. It's certainly very fast. I just observed that the model was derived from physics. I got the idea from mean tree path calculations in kinetic gases, but then I realized it's also in the sort of scattering experiments and those sorts of things. The diagram, of course, was conditional on one tree diameter, and obviously not all trees have the same, not all, but the density of trees varies depending on their size, and there's all sorts of complications like that. But it turns out if you add everything together, you get a sort of scattering cross-section, which is essentially the sum of the diameters of the trees that you're going to see. I said I'm skipping the maths. So I needed a proof of concept. That was all sort of done on paper and in my head. So I was living in North Melbourne at the time, and I decided to do a pilot study. So I went to this park nearby in North Melbourne and found a bunch of trees that I couldn't see through, or could almost not see through, and I tried to work out how many trees there were there. Now, you've got a whole lot of people playing around in the park, and I'm sort of looking through the trees like this, and then I just sort of pace up. And then I'd count them. That was the bit that was sort of a bit weird. But I came to a conclusion that you didn't have to have many trees before you couldn't see through them. Now, of course, the jungle was much more, had many more objects than park in North Melbourne. Some of them were quite big. That tree is at eye level and it's about 2 meters across. So needed to get some data. So that meant that the next step was to go to Tully. I insisted on going to Tully, which had a there was a nice consequence from that. They said, well, why can't you just tell them how to do it? And I said, no, I want to go and see it. I was collected at Townsville Airport, I think it was, by the colonel and his driver. And we drove an hour or something, maybe more, up to Tully. And at one stage, he turned around to me and he said, why did you insist on coming to see it? And I said, well, I always come to see things. I've got to look at it. It stops me making stupid mistakes if I don't actually see it. He wasn't very convinced. And I said, besides that, if we get sued and I have to appear in court, the first question they're going to ask me is, what did you see when you got there? And he said, I like that word. And I thought, what did I say? He said, you said we. And after that, he was my friend for life. So here's the team of highly trained observers. One in red here is me. I didn't want to get lost. And, here we are. Yes. And there's another one there in his jungle camouflage. It really works. He was standing about 2 meters away from me. So we tied up the jungle in red tape and counted the trees. I think one of the problems is this is hard to see is because there's some light on it, isn't there? Never mind. It looks good on here. And the conclusion was written there. Okay, if we figure that fewer than 1 bullet in a million goes beyond 1,000 meters. That's all sort of bold. I mean, that's a pretty conservative claim. And so I won't go into the statistics of that. it was only really a pilot study. So I suggested we should have a green template, same as the standard template, but just make it shorter. And that would make enough because the reduction from, was it 2,750 meters to 1,000 meters would bring all of those things into the allowed boundary. Of course, you'd have to have a rule that we're only allowed to use it where you had the sort of conditions of the jungle here. And then while I was there, sleeping under canvas, which was quite interesting in itself, a huge tent, absolutely huge. It was like being outdoors, except it was a tent. I mean, if you see what I mean, it had no walls. East Timor happened, and all of this has been forgotten as far as I can tell. The troops went off to East Timor, and I never heard any more about it. Is it statistics? No, I don't know. I mean, I've got the right sort of things, or designed a study, sort of, collected some data. Stochastic process model, and maybe it's just statistics. I was thinking like a statistician. All right, I've talked quickly, I hope, about another situation in contrast to that one. In that situation, I was on my own consulting to a large organization. This one, I was not on my own. I was part of a team consulting to a large organization, but in this case, a commercial company. And our job was to predict the individual selling prices, the selling prices of individual residential properties, and to be able to produce an estimate for each Australian property every day. And you can see that if we were successful, there'd be lots of applications for this. But the reason we were doing it was we wanted to construct indices, daily price indices, which people would issue contracts over for futures and things like that. And there'd be a value to compare it with. So it would be I don't know what the word is for it, but an index of record, if you like. So you could set that in your contract that what this value was is what you would settle your option on. Not that we were going to do any of that, except maybe later, but didn't get that far. So that was the real goal, the one in red. But the rest of it was useful too, and it has and is being used. What did the models look like? Well, the basic model, I call it the core model, looked like this. It was quite simple, really, a regression model. We have some transform of the price. I said it's log-like. Log curves over like that, and we made it curve over a bit more. So it was log-like, but up to a point, and then it dipped over more. So we were penalizing large prices, essentially. Well, reducing the influence of large prices. The attributes, how many bedrooms, size, land size, suburb it's in, stuff like that, was all in here. And there were hundreds of these. That's in the sigma beta IXI. There was a spatial smooth using GCV from R, generalized cross-validation, splines, and the MGCV library in R. And then we used a robust estimator to refit, essentially, well, you can read it, what I said. That worked eventually. It took a couple of years to sort all this out. There's a lot of stats in, when I was looking at this yesterday, I thought, actually, there's a lot of stats in there, in that statement saying smoothing stuff, getting the amount of smoothing right. You have to deflate house prices, and you need to do it locally because house prices change different amounts in different suburbs, and depending also on what sort of property you're talking about and stuff like that. Well, we were quite good. The median absolute error was 5%. I won't bore you with the rest of them. I can't change this because I don't have the data to create it anymore. So, but I can say more if you want. It's fairly easy to get within 10%. It's quite hard to get within 5%. Well, it was at the time, because of course the markets change and become more volatile and less predictable and so on. So the challenges what were the challenges? Well, one that was new to me, that I hadn't thought of. I'd thought of cleanliness and missing data and robustness. I thought of all of those things that are in red. But the bit I hadn't thought of, and it came as a surprise to me, it's obvious now, is that you have to apply that. If you have a holdout sample, you have to apply that to your holdout sample as well. And it didn't ever occur to me that that would be that's an issue. I'm used to the idea of having the sample, and you take a bit out, put it to one side, fit over here, and then test on that. But if you're doing it right, then that's got, the holdout sample's got many problems as the in sample. Anyway, that was just me not recognizing something that's blindingly obvious now. Computational demands were large, particularly at the time, because there was lots of data. Doing things like finding neighbors is a hard problem. And what we did with that was that, fortunately, the neighbors of a property don't change very much, don't change very frequently. So do that and store the results and update it once in a while. We kept hitting memory limitations of R running on Windows. And anyway, it was a task that took about 4 years to develop altogether, helped by a change in the database characteristics halfway through. It all had to be done again. How did that differ from the other one? Well, a great deal of money was at stake. At least I guess there was a great deal of money at stake at Tully as well, but the point was nobody actually owned that money. We all owned it, whereas this was owned by specific people, and they were concerned they wanted a return on their money. This meant there was a constantly pressure to be better and quicker than competitors of the clients. What puzzled me was that the clients accepted readily the need for out-of-sample testing. I thought, oh, you should have to explain that to people. And you know, they said, oh yeah, great. They also wanted us to do what I've called here delayed testing. And I suspect because they didn't trust us completely not to fake the results. By delayed testing, I meant you estimate values of properties at this date, you wait 3 months, see which ones sell, and see how right you were, the ones that actually sold. They could control that because they knew which properties had been sold, and they would give us the properties that had been sold that we were supposed to estimate. Weird things like the prediction intervals, which were asymmetric, they did not like that at all. They would not accept asymmetric prediction intervals. They wanted plus or minus, they wanted a standard deviation. They wanted to keep calling it a standard deviation. No, it wasn't, and because they were percentile based. Anyway, as I said, the thing that made it hard was the daily, that it had to be done daily. So, what was it like working in this? This was a small team. We used all of the team. We had 2 to 4 people, 4 PhDs, 1 in finance, 1 in applied maths, 2 in applied maths, one of whom was also more or less an actuary, and me. Mine was in pure maths, of course, as I've said earlier, but anyway, I think I could count myself as a statistician by then. Not everybody of the 4 of us were client-facing, and that was a sort of, some people are better at dealing with the client than others. So a couple of people we sort of kept out of the way. There were some irritating little things, like we could only use Windows. That was annoying. But little things were good. Money was good. Money was also bad because at the end of having done all this work, all the IP was ripped out of the company by a company takeover involving some of Australia's richest men. And we all lost our jobs and access to the IP and everything. Anyway, Not bitter, not at all. Comparing it with academic consulting, couldn't publish commercial in confidence, but like the defense stuff, you know, defense in confidence sort of thing. No public credit, no, they wouldn't, they're not acknowledged in any way. Though I do have 2 patents in my name, except I don't actually have them because they're owned by somebody else. But my name is on them. But, you know, contrast that, we were very well paid. Was this, what sort of work was it? The point I wanted to make here was the client company thought it was data science. They kept talking about it as data science, machine learning, data science. That's the words they used all the time. And in fact, they subsequently employed machine learners and data scientists rather than statisticians when they to modify the model. And in fact, we know they weren't any good because they didn't know anything about standard errors. But anyway, but nonetheless, I would say that was the breakdown I would give. And the reason for it doesn't add up, of course, is that I think A and B are essentially the same on projects like this. Was it consulting though? That's another question I suppose one could ask. Well, I would say it felt like consulting because there was constant demand coming from the client company. Are we there yet, basically? A lot of things had to be explained, and every time we went back to them, they had to explain them again. One of the pretty basic things. But the most interesting one, I think, was there was little understanding of science as an approach. It's often the case that your client doesn't understand what you're saying because you're speaking a different language. But this was something else. This was actually a mindset thing, I think. I think the idea that you try something, test it to see if it works, modify it, was not one that was in their mindset. They thought you ought to be able to say, what is the, how are we going to do this? What's the right, you know, do it this way. That's the answer. Not, oh, we'll try this and see if it works. But part of that was they didn't understand you couldn't just keep trying harder and harder and harder. We kept getting questions like, well, why don't you just leave out the properties that are hard to estimate? That you're going to get wrong. So, well, we don't know whether we got them wrong until we get the data that tells us what they sold for. So, well, we'll just leave them out. Well, we don't know. We can't identify them. And they kept saying if you tried harder, you ought to be able to get 100% accuracy, essentially, was what they were hoping for. Subsequently, I moved on to a university consulting service at Sydney. As I said, I was the university consulting service at Sydney for a couple of years. How is that different? Well, that's different because there's huge variety, particularly coming from HDR students. Do we call them that still? Yeah, so the acronym gets changed around, yeah. I mean, higher degree by research students. And the other thing that's different about this from the other sort of situation is that you can publish pretty much everything, at least in principle. It also depends, of course, that you're working with people. And if they're not that interested in publishing it or take too long, the consulting centre has been shut down before you finish the job. Oh, just to indicate the sort of variety, we start at the top. Computation of power and sample size for that's in the sort of the background. That was for a study of equivalence against a gold standard. That's why the word gold appears in there. Of course, we have surveys and Likert scales. This is a factor analysis plot about pairs of Spanish adjectives. There's all sorts of, these are all problems that walk through my door. This one is a random effects model. The time axis has disappeared beyond the bottom of the screen. And following individual subjects over time. The top right-hand corner is my favorite. This is a plot of scores on 2 different tests of musical ability. And the line is the ordinary least squares regression line. And it doesn't matter about the other thing. I explained it to the client, and it took me ages to understand why she couldn't understand what I was talking about. And the reason, I thought, okay, oh, I know what it is. I had to explain that each point was a person. When I said that, that still hadn't got anywhere. Usually that's a problem I have sometimes with people. They don't get that each point is a person. This was more fundamental because what she didn't realize was that, say, for this person here, she didn't understand that that meant that their score on this scale was about 57 and their score on this scale was about 47, and just had no concept of Cartesian geometry. Just didn't know. I mean, if I'd said east and north, and maybe it would have helped, I don't know. But once I got that, we solved it. I mean, then it all became quite clear. But it took me ages. I reckon it took me half an hour trying to work out what is it you don't get. Anyway, other problems. The variety, as I said, is this model better than that model on the same data, the broken stick versus a smoothed model? This was something I never had a chance to finish. This was about food insecurity, whether it's a diagram of factors influencing, subjective diagram of factors influencing that. We were going to do some sort of network analysis. And this is my latest project. The 24-hour clock, blue indicates spontaneous births, and this is the hour of birth. As compared with the red ones, inductions. The top is before an intervention and the bottom is after an intervention. And the question is, has the distribution of times of birth changed as a result of the intervention, which is about inductions, and the blue circle tells you what's happened if you don't do anything. So the control group. The only reason that's an interesting problem to me was I scratched my head and I thought, oh yes, that's Truskell, Wallace, or Wilcoxon or something, you know, one of those sort of things for testing distribution display. And I thought, hang on, but no, it's wrapped around a circle. You have to do something else. So I learned something. And so, you know, there's a few tests of that. There's one by Rao, which is uniformly most powerful and stuff like that, and gives absolutely rubbish results in this case. But I don't know why. Anyway. I should be as quick as I can through this. So a couple of things I've learned. Basically, the subject matter doesn't matter. Okay, I mean, it does matter in a sense, like morally it might matter to you. I won't work for a gambling company, for example. I love that quote from Brillinger. And really, I think, of course, the environment that you work in is crucial for your enjoyment of how you work and stuff like that. But I don't think the environment actually affects what you have to do technically, though it may affect how much resources, you know, what resources you've got to do it. I've learned consulting can be really rewarding. I learned stuff, like about the distributions on the circle. And sometimes you have a good feeling about having done some good. If you're lucky, you get paid. And the interpersonal relations are great. I mean, that's, you know, sort of really nice. I've met some really nice people doing this sort of stuff. These are pretty obvious. I will say no more. Life's just a bit like that. I'll just mention quickly, because I love this quote from Tukey as well. Where's it taken me? Well, physically, it's taken me to a jungle. It's taken me to an IVF operating theatre. It's taken me to Switzerland, got horse stud, the city, underneath E1, I mean, modelling about gold prices, and about improving ground. The reason I put that one in was because ENIAC was, well, I went there to talk to people about noise propagation, when you have temperature inversion, you get a sort of waveguide over water. And so when you set off a bang here, it travels a long way and annoys the people long distance away, apparently. They knew about it and I didn't. We got nowhere. But also, rapid improving ground is where ENIAC, or the prototype for ENIAC, was built. But anyway, I saw a piece of ENIAC while I was there, which was nice, which is one of the first computers, valve computers. Garrett Burkhoff, he was the man who developed the ricochet laws that I was using, and that was nice, and he worked there. But I also knew him because he's a co-author on Burkhoff and McLean, categories for the working mathematician, which went back to my days when I was doing my PhD. So even pure mathematicians can do statistical models as well. Dungog and other, what was the other thing? Dungog, yeah, well, Dungog, you may know, is a small town in New South Wales Valley, the Hunter Valley. I had to learn things: option pricing, clinical trials, Bayes, ODEs and PDEs and SDEs. I don't think there's any other sorts of DEs that I've left out of that. I won't go into that. The technical things where I developed new ideas for myself are large-scale simulations and some stuff about many short Markov chains and reversibility. Just what I wanted to say really is not what those things are, but just that there are intellectual challenges here, and some of them are interesting. In my view, I promised I'd say something about this, so I'll bore you quickly with this. I don't think there should be any difference between statisticians and data science. I think it's just about marketing and employers. So if they're going to employ me as a data scientist, I don't care. If that's what they want to call me, they can call me that. If they want to employ me for my folk dancing skills, which don't exist, I'm happy to be called a folk dancer. And it's true, there's shonky data science and there's overhyped data science, but there's also some good stuff coming out of that part of the world too, like not the fake news channel, but convolutional neural nets, random forests, Shapley values, stuff like that, which is interesting and sort of, I was like left field, I suppose. But the basic thing is you can't do data science without the statistics, and statistics need computing skills and new models and algorithms, stuff like that. So basically what it boils down to, my point is that we need symbiosis. Thank you.